Let's say you were to have some sort of food like porridge or something, whatever, and you shift it towards you in that direction. You may notice that it starts to bunch up closer to you and spread out at a distance on the opposite side. So this is away and this is towards. And if we were to represent this distance here by lambda, you can see that away from you, this lambda distance has increased, but towards you, it's gotten a lot smaller. On the opposite side, the lambda has increased, which, and if you remember from waves, lambda is inversely proportional to frequency, so the frequency will have decreased, and towards you, the lambda value decreases, so the frequency increases. And this here is an effect known as the Doppler effect. Now, one day some scientists went off and did an experiment, and they were measuring the hydrogen spectrum, or a spectrum of something from a object in space. And usually from a lab, they look at the hydrogen spectrum, and it may look something like this. But when they observed the hydrogen spectrum for a object far, far, far away, they realized that the hydrogen spectrum looked like this. And just to be clear, towards the right is increasing wavelength, and the bottom one is their measured spectrum from a distant source. They noticed that all these lines, these emission or absorption lines, had been shifted by a specific amount. And this here was the discovery of the Doppler effect. The Doppler effect shows that almost every single source has been shifted towards a side with increasing wavelength. And we know that if the wavelength is increasing, this source is moving away from us. And this is known as red shift, where the source is moving away from us. And this therefore causes an increase in wavelength. And we call it red shift because red has the longest wavelength for visible light. And there is a term called blue shift, which is where the source is moving towards us. So this is decrease in lambda. And now this Doppler shift denoted by Z is equal to the change in wavelength over the original wavelength. And this ratio has actually been shown to equal the speed at which your object is moving away from you over the speed of light. This here is your Doppler equation, where C here is your speed of light, V is the speed of the object. If we looked at our spectrum, one from the lab and one from the source, let's say for this example, the wavelength of that particular line had a value of 710, but it had been shifted from the source to a value of 720. Well then, if you look at our Doppler equation, this value here would be equal to 720 minus 710, and this value here would have been equal to 710. Now actually what happened is, as time went on, and they kept measuring the wavelength emitted by this source, they realized that this kept getting more and more red shifted. Now this means that the speed of this object was increasing and increasing over time. And this actually points to evidence for an accelerating universe, or a universe that is expanding at an increasing rate. But that's something we will come back to at the end of the video. For now, let's look at more of this Doppler shift, this red and blue shift. And a good way to look at it is through a binary star system. Now, binary star system is where two stars are both orbiting each other around a common point here. So they're both orbiting around that fixed point. And let's say we are an observer on Earth, and Earth is down here. So at position 1, where A is currently right now, the planets are moving towards us, and at position 3, they are moving away. And at position 2 and 4, they're moving left and right to where we are viewing. Now, these stars are going to be emitting some light, so we can actually measure the wavelength emitted by each star. When either star is at position 3, it is moving away from us. And we know that if something is moving away from us, it's going to cause a red shift, or in other words, an increase in the wavelength. So at position 3, we're going to have a wavelength that is higher than what we expect. Now on the opposite side, at position 1, we're going to have a wavelength that is lower than what we expect as the star is moving towards us. And this is due to something, as we've discovered, called blue shift. So at position 1, we're going to have a wavelength down there. Now at positions 2 and 4, the star is moving in a direction that is neither towards us nor away from us. So therefore there's going to be neither a blue shift nor a red shift. So what we'll actually see is that the wavelength emitted by one of these stars is going to look something like this. At positions 3, we're going to see that there is a red shift, or a larger wavelength. At position 1, we're going to see that the wavelength has decreased, and at positions 2 and 4, we're going to see that the wavelength is not being shifted at all. So if we were to measure the wavelength of light emitted from one of these stars, it would look like something that is shown by this graph. Let's look at a binary star system where one star is hotter than the other. And let's say we were measuring the apparent magnitude of this total system. Well, we know for starters that when the stars are at position 1 and position 3, they are both going to be visible in the sky, i.e. we are able to see light emitted from both of them. So we know that when they are at positions 1 and 3 respectively, we are going to receive a greater apparent magnitude. Or if the stars were at positions 2 and 4, one star is going to be in front of the other one. So the light from one star is actually going to be blocked a bit by the other one. So this means that at this point we're going to see a lower apparent magnitude. So what we're going to see is as these stars orbit around each other, we're going to see that there is going to be a periodic change in apparent magnitude that will look something like this. Remember that for apparent magnitude, if there is a brighter apparent magnitude, the number will be lower. So 2.5 means that it is brighter than 2.7, which is brighter than 3. And these are just some arbitrary values that I've selected. Now when the stars are at position 1 and 3, they are both visible in the sky, so we're going to be able to see a brighter apparent magnitude. And that is what happens here. At positions 1 and 3, we're going to see these brighter spots in the sky. So we're going to see more apparent magnitude received from these stars. As you can see, there are these periodic dips when one star is in front of the other. Now it turns out for when you have a larger dip, the cooler star is in front of the hotter star. And when you have the smaller dip, it's where the hotter star is in front of the cooler. And when I mean in front, it's basically closer towards the Earth. Now you may need to recall this sketch for your exam. Let's go back to our spectrum. What some guys have measured. So they've measured two different stars which have different Doppler shifts. Now remember our Doppler shift equation, that is Z is equal to change in lambda over lambda, and that's equal to V over C. And these have all been redshifted. So what this means is star 2 is moving at a greater velocity than star 1. And what these guys also measured was that in general, any star that has a greater Doppler shift is further away. That means that for distance, the star 2 is also further away than star 1. And that's not just for two specific cases, but for a general case involving many stars or many systems. And this got scientists pondering, well, the further away a star or a system is, the faster it also seems to be moving. So they came up with this relationship where V is equal to H naught D. V here is your receding velocity. D is the distance from star to Earth. And H naught is your Hubble's constant. So they derived a linear relationship between velocity and distance. Things that are further away from us seem to be receding or moving away at a velocity that is greater than things that are closer to us. And this Hubble's constant h0 has a value of 65 kilometers per second per megaparsec. And this value is given to you in your data booklets. Now let's kind of look at this Hubble's constant and what it actually means. Well, let's try and simplify these units because these look a bit complicated. So 65 kilometers per second per megaparsec is equal to 65 times 1000. Or 65 kilometers per second is equal to 65 times 1000 meters per second. And 1 parsec is 3.08 times 10 to the 16 meters. So 1 megaparsec is that times 10 to the power 6. And this gives you a value of 2.11 times 10 to the minus 18 per second. To see that this looks like something sort of like a 1 over time. So let's see what this time means. So t is equal to 1 over h0. And this 1 over time is 1 over 2.11 times 10 to the minus 18. That's equal to 4.738 times 10 to the 17 seconds. That's a very long time. So let's convert that into years. So you do 4.738 times 10 to the 17. There's 60 seconds per minute, 60 minutes per hour, 24 hours in a day, and 365 days in a year. So that's going to give you 1.5 times 10 to the 10 years, or 15 billion years. So 1 over h0 is equal to 15 billion years. And this is roughly equal to the age of our universe. It also means that this constant h0 is constantly changing. They're always finding new values for this h0. But it will give you a rough estimate as to what our age of the universe is. The fact that we know that everything that is further away from us is moving at a faster velocity is actually one of the evidences that we can use for the Big Bang Theory. The first piece of evidence that we can discuss is redshift. Now, in every direction that we look, we can see that everything is moving away from us because everything is redshifted. And this kind of points to the fact is, well, if everything is moving away from us, and as time goes on, things are continually moving away from us, this means that there would have been a point in time where if you reversed it, everything was at one single point. So redshift is an evidence for the Big Bang Theory. And redshift actually comes from the expansion of space. Redshift actually isn't from the Doppler effect. It's actually because space between planets or space between galaxies and stars is spreading out or expanding. And that's what causes the redshift that we see from galaxies or stars. Another thing is called cosmic background microwave radiation, otherwise known as CMBR. Now, what people measured was when they looked out into space, they kept receiving this sort of background radiation in all of their measurements. And this background measurement was existing in every single direction they pointed in. Now, the only explanation for this radiation was it was remnant radiation from the Big Bang. And as the universe expanded, we know that this radiation would also get redshifted, i.e. the wavelength of this radiation would have increased. So at the time of this Big Bang, this radiation would have had a much shorter wavelength, as was theorized. And due to redshift, it now has a wavelength in the range of microwave radiation, which is proof for the Big Bang. Now, the last piece of evidence for the Big Bang is the relative abundance of hydrogen and helium in the universe. Now, in the early universe, it has been calculated that there should have been a ratio of hydrogen to helium of a ratio of 3 to 1. And this ratio is still present to this day, which again points towards evidence of the Big Bang. Now, just as a little side note, just one piece of extra information, we have also found out that the universe is not only expanding, it's expanding at an increasing rate. And this might seem weird because there's lots of matter in the universe, so surely everything will have some sort of gravitational attraction towards each other. So surely the expansion of the universe must be slowing down. But the reason why we have an accelerating expansion is due to something known as dark energy. Now, scientists don't know what this is fully yet, but we do know that it exists and that dark energy is the reason for our accelerating expansion of the universe. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.